Hello and welcome to week 4. And this week we're going to go over electromagnetic induction, which is chapter 17 in the textbook. So let's get started here. So we know that the electrons are very important in everything with electronics, especially magnetic movement. And so if we know the direction of the current flow, we can determine um, the magnetic field. So the way this is done, Oersted discovered this relationship, and then Faraday observed that electricity could be produced using magnetism. So first one noticed the current and magnetism, and then magnetism and voltage and current. So Faraday observed that if a conductor was passed through a magnetic field, a voltage was induced. And if the conductor was part of a complete circuit, a current could flow as well. This is known as electromagnetic induction, which is really the principle of generating AC power, right? Now we know that a magnetic field is generated by a current carrying a conductor. And then the relationship between the direction of the magnetic lines around a conductor and the direction of current is determined by means of what's known as the left-hand rule, with the assumption that current flows according to electron theory, which is what we teach in this class, right? So if you grab a conductor in your left hand with the thumb extended in the direction of the electron flow from the negative to the positive, your fingers are going to point in the direction of the magnetic field lines. So if you do that here, you notice that the magnetic lines are circular as the field is symmetric. Now, what's funny is this picture is showing the right hand, right? Not the left hand. Let me check the book real quick. Yeah, so now let me change this slide real quick. Hold on. All right, hold on. I'm just getting this slide updated here. Hmm. All right, so that looks better. That's the left hand rule with the left hand, not a right hand on there. It's funny. I never noticed that the older copy of the book had the wrong picture. But notice here the left hand, if current is flowing in this direction, the magnetic field or force will be induced in that direction. All right. So let me get my pen back on here. All right. So the current, of course, is going this direction, and then the flux lines are going around in this direction. All right. So the strength decreases inversely as the square of the distance from the conductor. So in addition, the current needs to not be within a conductor. So there's that. Now, if the direction of the current changes, the resultant magnetic field reverses as well. So when parallel conductors carry current in the same direction, the magnetic field lines of force combine and increase the strength. If the current are in two parallel conductors is in opposite direction, they will repel each other. So in this one, they combine, right? They add forces, and in this one, they repel. Okay? Now, bending a straight conductor into the shape of a loop or several loops has two effects. First, the magnetic field lines are denser inside the loop. Their number is the same as in a straight conductor, but now they are concentrated in a smaller space. Also, the lines inside the loop are all in the same direction. Now, you can vary the intensity of the current through a loop by changing the amount of current. So all this is coming into play with us developing a magnetic coil that can be used to induce current into our circuitry. Okay, so determine the magnetic polarity. Use the left-hand rule by grasping the coil with the fingers of the left hand curled around the coil in the direction of the electron flow. The thumb points in the direction of the current. So if you know the magnetic flow, but you don't know the current flow, you can see that here the current is going to go in the electron theory, which is negative to positive. All right? And the polarity depends on the direction of the current flow and the direction of the windings. And if they reverse, the poles will reverse. Now, Faraday discovered that a voltage is induced by magnetic flux cutting the turns of a coil. And this exists between the flux and the coil, and this is known as flux linkage. And the amount of induced voltage depends on the number of turns on the coil and how fast the flux moves through or across the conductor. So either the flux or the conductor can move. The important point is that there is a relative motion between the two. So you can either move the flux or you can move the conductor. Either one will induce the voltage. And these magnetic fields, when they move, are known as generated voltage. So the principle of generator is related to this. Now, the number of, where's my pointer? There it is. So there are three basic factors that determine the magnitude of an induced voltage or electromagnetic force. The number of turns in the coil, the strength or flux lines of the magnetic field, and the relative speed or rate of change between the coil and the magnetic field. Now, it's important to realize that the flux must be moving. So you can't just have a voltage induced by a magnetic field that's stationary. Something has to move, either the conductor or the magnetic field. Okay. Now, mathematically, this can be calculated where the induced voltage equals the number of turns times the change in the flux divided by the change in time. So this delta is always referred to as the change. All right. So if we ask this question, what is the induced voltage if a magnetic flux of 1,000 microwebers cuts across a coil of 2,000 turns in 1.1 seconds? You take 2,000 turns and you divide that. Why is my mouse? So you take 2,000 turns times 1,000 microwebers divided by 0.1 seconds, and you end up with 20 volts. So that would induce 20 volts into our circuit. Now, another discovery was when Lenz concluded that the current induced in a coil due to a change in the magnetic flux is such that it opposes the cause producing it. This is known as Lenz's law. And the induced voltage in a circuit causes a current to flow, such as magnetic field opposes the motion that generated the induced voltage. So here's some pictures that show the magnetic field, and the induced current is going to go in the direction based on the magnetic field. So if this changes, the current is going in the other direction. All right. Now, an AC generator or an alternator is an example of a device that converts mechanical energy into electrical energy. And the voltage depends, again, on the strength of the magnetic field, the speed that the conductor is moved, and then the length of the conductor within the magnetic field. So, and then the polarity of the voltage depends on the direction of the flux lines and the directions of the movement. And the left-hand rule still applies. So you extend the thumb, forefinger, and middle finger to the left hand at the right angle to one another. And that determines the motion of the conductor is your thumb, the current is your index finger, and then the flux, or the current, is your middle finger, and then the flux is your pointer finger or your index finger. Okay, so here's the current, here's the flux, and then here is the current. Now that's the motion of the conductor. All right, so if we move this conductor up through this magnetic field, it's going to induce the current in that way. All right, so if we have a pole here, a north and a south pole, which will have the magnetic field, and we rotate this conductor, it's going to generate current through our wires, and we can measure it here. Okay, so the rotation of the wire loop inside the magnetic poles will produce an induced EMF in the loop, and this loop is called the armature. So this loop here is the armature. All right. And as it rotates, the angle is going to change, and we will get our one complete revolution here will give us one complete sine wave. So that's the elementary AC generator. Now, all electrical generators depends on the principle of magnetic induction, and the part of the generator that produces the magnetic field is called the field. The part of in which the voltage induces the armature, and the rotor is the part that rotates, and the stator is the part that remains stationary. So here's the stator coil or core, and then inside of it we'll have the rotor. So the rotor will move. So if you have a little power generator, the stator is here, and then so you'd have your engine here, right? Your gas engine, and it would rotate the rotor, which is here, that rotates inside of it, and it will induce a coil or a signal on your stator. So the windings may be wired to provide single or three-phase voltage. Three-phase is very common because of its efficiency, and it contains three single-phase windings spaced so that the voltage induced in any one phase is displaced by 120 degrees from the other two. And the stator coils are joined in either a Y or a delta connection. So here's the delta connection, here's the Y. All right? And then the DC generator is similar to the AC generator, with the exception of having a commutator instead of brushes, and the commutator produces pulsating DC instead of AC. And the different windings could be series field, shunt field, or the series shunt field. So those are different DC generators. Now, in a generator, you're going to have losses due to the I squared R, or copper losses in the winding, or the eddy current losses or hysteresis losses due to the magnetic friction. Remember last week we compared a magnetic circuit to a regular electronic circuit, and the opposition to the flow of magnetism is what's known as the hysteresis loss. It's like the resistance. All right. Now, anytime a current flows through a resistance, there will be power dissipated in the form of heat. And this is true of the windings in the armature. So to minimize this, the larger diameter wires are used to reduce the resistance. Okay, and then the core of the armature is made of soft iron. And when a conductor moves through a magnetic field, a current is produced. These currents in the iron itself are called eddy currents, and this can cause power to be dissipated in the form of heat as well. To minimize eddy current losses, the core is laminated and insulated between laminations. So if you look inside of a generator on the stator, it will all be laminated to reduce those eddy currents. Now, in chapter 16, we talked about hysteresis, which is the friction caused when the dipoles are moving back and forth, right? They're north and south are switching. So that's going to create friction, and that can cause power to be dissipated in the form of heat as well. And to compensate for that, silicon steel laminations are used in the armatures, and the heat treatment causes an annealing process that reduces the hysteresis losses. All right? Now, the motor is the opposite of a generator. It converts electrical energy into mechanical energy. So the generator takes movement and generates electricity, and the motor takes electricity and generates movement. Now, motors use the right-hand rule. So instead of the left-hand rule, now we're going to use our other hand and get the right-hand rule. All right? So in the right-hand rule, the motion is your thumb, the induced EMF is your index finger, and the field is your your middle finger. All right. Now, several types of DC motors. In a series motor, the field windings are in series with the armature coil, and it has a starting torque, and the speed varies depending on the current through the armature. And then a shunt motor has the field windings in parallel across the armature coil. So the field strength is independent of the armature speed or current, and the speed varies only slightly. All right, so the motors there's different types of motors that you'll see in electronics, and in your Elect 54A, you'll work with some motors in that course, right? It varies. Now, compound motors has one set of field windings and is connected in series with the armature, and one set is connected in parallel. And then the speed and torque are both a combination of the series and the shunt motors. And then you have stepper motors that are kind of a niche where they're commonly used in measurement, so only move one step at a time. Where you see that most commonly is in your inkjet printer. So when it's moving back and forth to print, that's a stepper motor. Right? Now, some of the features of a stepper motor, one, it's brushless. So the commutator and brushes are common points of failure with other motors. So the stepper motor doesn't have that. And then it has an excellent response to startup, stopping, and reversing. All right, so I'm gonna leave some of this material for you to look at. You can read up on the DC motors. So here's a typical stepper motor that's found in your inkjet printers, and there's also brushless DC motors, which have some higher dynamic response, higher efficiency, longer life, and they're really quiet. So those are very common. Here's some AC motor information. So I'm going to leave the rest of this for you to read, which, only a few more slides here. But I do want to talk about the homework this week. I'm going to say, don't say. So the homework this week, let me pull that up. And homework 3, and again, remember, this is from chapter 16. So go back and read chapter 16, and you can pick this up during the beginning of week 4's lab, this week's lab, and then you can hand it in at the start of next week's lab. All right. So that's it for this week, and I will see you online. Bye.